In this lesson, we're going to be proving trigonometric identities, and by the end, you'll be able to prove them using primary trig identities and without using the primary trig identities. A trigonometric identity is an equation involving trigonometry that is true for all values of the variable, meaning it has a left side that's equal to its right side. And to prove trigonometric identities, we're just going to prove that the left side is equal to the right side of the equation. Let's start with the primary trigonometric identities. If we create an angle theta in the first quadrant of the Cartesian plane by drawing a point xy, the terminal arm of that angle is this, and the initial arm of that angle is down here at the x-axis. We can use this to create a right triangle. X is the measurement of the bottom side of this triangle, and y is the measurement of this side of the triangle. We can use r to represent the hypotenuse of this right triangle. So we're going to use this right triangle to determine our primary trigonometric identities using x, y, and r. We know that the sine of any angle is the opposite side over the hypotenuse, so in this case it's y over r, and we know the cosine of any angle is the adjacent side over the hypotenuse, so in this case it is x over r. The tan of any angle is the opposite side over the adjacent side, so in this case it's y over x. So these are known as the primary trigonometric identities. We have sine theta is equal to y over r, cos theta is equal to x over r, and tan theta is equal to y over x. We can use our primary trig identities to prove other identities, so we're going to be proving tan theta is equal to sine theta over cos theta using these primary identities. Trig identities have a left side and a right side, and to prove trig identities, we need to show that the left side can simplify to the same thing that the right side can simplify to. So we've proved this already before, but we're going to be proving it again with our primary identities. So on the left side, we have tan theta, and on the right side, we have sine theta over cos theta. So we need to separate the left side and the right side. From our primary identities, we know that tan theta is equal to y over x. So on the left side, we can replace tan theta with y over x. And then on our right side, we know that sine theta is equal to y over r. So we can replace this sine theta with y over r. And we also know that cosine theta is equal to x over r. So we can replace this cos theta with x over r. Now y over r is being divided by x over r, and that just simplifies to y over r multiplied by the reciprocal r over x. These r's can cancel each other out, so we're going to be just left with y over x on the right side. And that's the exact same thing we have on the left side. The left side is also equal to y over x. So our left side is equal to the right side. And that's what we want. That's what we want to prove. So this just means that this trig identity is true. And we're done. In the next example, we're going to be proving this identity using our primary identities. And this is known as our Pythagorean identity. So let's start by breaking up this identity into the left side and the right side. So on the left side, we have sine squared theta plus cos squared theta. And on the right side, we just have 1. On the left side, sine squared theta plus cos squared theta is the same thing as sine theta squared plus cos theta squared. And from our primary identities, we know that sine theta is equal to y over r, so we can just replace this sine theta with y over r. And cos theta is x over r, so we can replace this cos theta with x over r. And now we need to make sure we square both the numerator and the denominator, so this just becomes y squared over r squared plus x squared over r squared. So I have the same denominator and I can combine these. So the left side can turn into y squared plus x squared, and that's all over r squared. If we take a look at the right side of our identity, it's just equal to 1, and it can't really be simplified any further. It's just 1. But we want to find a way to get the left side equal to 1. So from our last page, when we had that diagram of a right triangle, x is just on the bottom. This is angle theta, y is on the right, and r was our hypotenuse. And since this is a right triangle, we could use Pythagorean theorem. X squared plus y squared is just equal to r squared. So we can now replace y squared plus x squared with r squared. So the left side is equal to r squared over r squared, and we just need to make a little note to show where we got that. So r squared is equal to x squared plus y squared, and r squared over r squared is just equal to 1. So now the left side is equal to the right side. And we're done. Now let's get a little more comfortable with our Pythagorean identities. So we've already proved this Pythagorean identity with the primary identities, but why does it work? Well, we've already learned about the unit circle, and we learned about a point xy on the unit circle. We know that for any angle theta on the unit circle, cos theta is this bottom side here, which is just x, and our sine theta is this side right here, which is y. And since this is a unit circle, our radius is equal to 1. From the Pythagorean theorem, we know that a squared plus b squared is equal to c squared. So from any triangle, x is just down here, so x squared plus our y squared is equal to the radius squared. And we know from the unit circle that cos theta is just x, and sine theta is just y, and 1 would be our radius. And that's where our Pythagorean identity comes from. That's why it's true. Sine squared plus cos squared is equal to 1 squared, which is just 1. This sine came from our y squared, and this cos came from our x squared, and 1 was just the radius. So this is our most common Pythagorean identity. There are 2 more that we're going to derive, and we would derive them by just dividing by sine and then dividing by cos. So if we take our original Pythagorean identity and divide everything by sine squared theta, so that means I'm dividing this by sine squared theta. I'm going to divide cos squared theta by sine squared theta. And I'm going to divide 1 by sine squared theta. Sine squared theta divided by sine squared theta, well, that's just 1. Cos squared theta divided by sine squared theta is the reciprocal of tan, so this is cotangent squared theta. And 1 over sine squared theta is the reciprocal of sine, so this is just cosecant squared theta. And that's it. This is our second Pythagorean identity. Now let's take our original Pythagorean identity and divide everything by cos squared theta. So we need to divide sine squared theta by cos squared theta by cos squared theta, and divide 1 by cos squared theta. And sine squared theta divided by cos squared theta, well, that's just tan squared theta. Cos squared theta divided by cos squared theta is just 1. And 1 divided by cos squared theta is just the reciprocal of cosine. So that's secant squared theta. And this would be our third Pythagorean identity. So these are all our Pythagorean identities listed below. We have our first one, our most common one that we're probably going to use, sine squared theta plus cos squared theta equals 1. And then now we have derived these 2 Pythagorean identities, so we can start using these when we're proving our trig identities. There are a lot of techniques that you can use when you're proving trig identities. You always need to separate the left side and the right side, and remember, always start with the side that looks more complex first. You should also try changing everything in terms of sine and cosine. You can substitute in your Pythagorean identities. If you have multiple fractions, you might want to combine them by adding, subtracting, multiplying, or dividing them. Try factoring if you can. And sometimes you might even need to multiply by the conjugate. In the next trig identities, we're going to be proving them without using the primary identities. Remember, you always want to separate your left side and your right side. You don't want to keep this together because it's not like you're solving an equation. So you don't want to do something like get rid of this denominator by multiplying everything by sign. You cannot do that when you're proving identities, so you need to keep them separated. So on the left side, we have cos x times tan x, and that's all over sine x. And you want to start simplifying or maybe substituting anything you can in this. So we always want to try to change everything in terms of sine and cos, but we have a tan x here. Well, we know that tan x is equal to sine x over cos x, so we can replace that tan x. So our left side is cos x, and that's multiplied by sine x over cos x. And this sine x on the denominator stays the same. And if you're making a substitution, you always want to show why you're making that substitution. So you need to put these 3 dots in the form of an upside down triangle. This symbol means because or since. So because tan theta, or tan x, is equal to sine x over cos x, we could make that substitution. And now you just need to start simplifying. So cos x is being multiplied by sine x over cos x. We can cross out this cos x. So then we're just going to be left with sine x over sine x. And sine x over sine x is just 1. So on the left side, we're just left with 1. And on the right side, we just have 1. So therefore, our left side is equal to our right side. And we're done. We've proved this identity. So here's the next identity we need to prove. On the left side, we just have cos x, and we can't really do anything with that. Our right side is definitely the more complex side, so let's start working with this right side. We have 1 over cos x minus sine x times tan x. And we have a tan x there, so we can switch that in terms of sine and cos. So our right side is just going to be equal to 1 over cos x minus sine x times sine x over cos x. And we can make that substitution since we know that tan x is equal to sine x over cos. So on the right side, we can do this multiplication. So this should just become 1 over cos x minus sine x squared over cos x. And we already have the same denominator. We have a denominator of cos x. So we can rewrite this as 1 minus sine squared x over cos x. Well, looking at what we have left, there's a sine squared x here. Well, do we know an identity that involves a sine squared x? Well, that's the Pythagorean identity. Sine squared x plus cos squared x is equal to 1. Well, is 1 minus sine squared x equal to anything? In our Pythagorean identity, if we move the sine squared x over to the other side and subtracted it, 1 minus sine squared x is equal to cos squared x. So that means we can just replace 1 minus sine squared x with cos squared x. So we have cos squared x over cos x. And we can do that substitution because of the Pythagorean identity. And using our exponent laws, cos squared x over cos x is just equal to cos x. And this is exactly what we have on the left side. So our left side is equal to the right side. And then we're done. We've proved this identity. So here's our next identity, and the left side definitely looks a little more complicated. So let's start with that. Our left side is equal to sine squared x over 1 minus cos x. Now we have a sine squared x, and we already know that our Pythagorean identity has a sine squared x. So our Pythagorean identity is sine squared x plus cos squared x is equal to 1. So let's try using that. Notice on our right side we don't have a sign, so let's actually get rid of that sign. If we rearrange the Pythagorean identity and subtract cos squared x, we would just get sine squared x is equal to 1 minus cos squared x. So let's replace this sine squared x. We're going to replace it with 1 minus cos squared x. And that's because of the Pythagorean identity. So we have 1 squared x minus cos squared x, and that's just over 1 minus cos x. And we need to somehow get 1 plus cos squared x. But on our left side, we just have two subtraction signs. Do you notice anything about our numerator? Is there anything special about our numerator? 1 minus cos squared x. Well, let's try factoring this. We have two terms here, 1 and cos squared x. And each term is actually a perfect square. Two perfect squares that are being subtracted, so this could be a difference of squares. Well, it's definitely a difference of squares. So when we factor out that numerator as a difference of squares, we're going to get 1 minus cos x, and that's going to be multiplied by 1 plus cos x. And that's all over 1 minus cos x. And we have something common in the numerator and denominator. We can cross out this 1 minus cos x. So that just leaves us with 1 plus cos x on the left side. And on our right side, we have 1 plus cos x, which is exactly the same thing. So our left side is equal to our right side, which means we have proved this trig identity. So try proving the next trig identities on your own, but if you do get stuck, you can always just watch the video. Trig identities are like puzzles. If the first strategy you try doesn't work, you can always start over and try a different strategy. And this definitely requires practice. The more trig identities that you do, the more you'll get the hang of it, and it'll just come easier to you.